So for electric potential energy, okay, electric potential energy, that's also known as EPE. Okay, but for the sake of this lesson, we're going to use the variable PE sub E, because basically this is potential energy. Okay, so you can also write this as PE, which is just actually potential energy. Okay, so this is the energy required for you to move one charge from one point to the next. Okay, then since this is energy, the unit of that is in joules. Alright. Then we have electric potential. So this is the capability of a charge to move. If this is the energy required, this one is the potential or the capability. Okay, to make things simpler, this is also known as voltage. Alright, so since that's voltage, our variable for that is V. Okay, and our unit for that is in volts or V. Alright, so for electric potential difference, that's also the same as this one, so that's in volts or V. Alright, so first let's try to list the equations first so that you will be familiar. So let's state the equations that we're going to use for this particular topic. So first we have potential energy, or electric potential energy, is equal to QED. Alright, so this ED is electric field times distance, and from the definitions that we have learned from the topic earlier, voltage is equal to electric field times distance. So this is what we call as potential gradient. So if you remember the simulation that you did, these are the green circles that surrounds your point charge. Then at the same time, since V is equal to ED, you can substitute this here, so that would make potential energy or electric potential energy is equal to QV, and consequently voltage would also mean potential energy over Q. Alright. Let's try to, for our first problem, let's try to solve it. Okay, so we have an electric field. By the way, the unit for electric field, which is newtons per coulomb, can also be rewritten as voltage per meter, as you have discovered from the simulation that you did. So our electric field for this is 525 volts per meter. Okay, then the distance between these two is 11 millimeters. Okay, then the question is voltage. So So the required is voltage. Alright, so equation for that, so voltage is equal to this one. Okay, really simple. Alright, so that would be electric field times the distance. So for the solution, let's try to, it's just actually substituting the values, right? So that would be 525 volts over meters times the distance, which is 11 millimeters. So then let's change this to base SI, so that would be 525 volts per meter times 11 times 10 raised to negative 3. So this is the multiplier for milli times meters. Okay, then that would mean we can cancel this, since this is in the new denominator and this one is on the numerator. Then that's it. Just input the values on your cycle. That would be 525 divided by 11 times 10 raised to negative 3. It's equal to 4 point. So can you see the value? So that would be 4.77. So round down, so stayed the same. Right, so that would be 4.77 times 10 raised to 4. Then the unit would be volts. Alright. So for another problem, let's try to solve it. So our given, first we have a charge negative 7.7. Write the variable first, so that's negative 7.7 microcoulombs. Then we have a potential, electric potential, so that's voltage, which is 65 volts. Alright, required is potential energy, correct? Okay, so since according to the problem, how much energy is required? Okay, so for the equation we have PE equals to QV. Alright, then that's it. Just substitute the values. So that would be potential energy is equal to, we have negative 7.7 microcoulombs times 65 volts. Okay, then let's convert this first to base SI, so that would become PE is equal to negative 7.7 micro is times 10 raised to negative 6 coulombs times 65 volts. Okay, next let's change this to different SI units, because as you can notice, you cannot cancel any of it, and volts coulomb is not a proper unit for energy. So instead, we're going to do is potential energy is equal to, so just copy negative 7.7 times 10 raised to negative 6 coulombs. Then volts can also be expressed as joules per coulomb. In this case, you can cancel coulombs, and you can notice that the remaining unit is in joules. Then after that, you can proceed on inputting your values to your cycle. So let's do that. So we have negative 7.7 times 10 raised to negative 6 times 65. So our answer would be here. Alright, so round up, so that would be negative 5.01 times 10 raised to negative 4 joules. So that's the value of our potential energy. But as we have learned from the beginning of this lesson, we actually don't need the negative sign, so just find the absolute value. So the final answer would be the potential energy is 5.01 times 10 raised to negative 4 joules. And that's it. Okay, for another example, we have given, so we have 45 volt battery, so we have this one. Okay, then we have the electric field, which is 1900s or 1900 volt per meter. Okay, required for that is what's being asked, how far apart, so that's distance. Okay, so since you can see these values, we can now say that the equation necessary is V is equal to EB. Alright, so let's solve for that. We have before solving, so let's try to derive first. So what we need is distance, so divide both sides by E. So that would cancel E on the right side, so that's D is equals to V over E. Then now you can substitute the values. So we have D is equal to, what's our V, 45 volts divided by 1900 volt per meter, so cancel the voltage, then reciprocal this one. Okay, so for your answer, so this is really quite easy. Okay, so we have 45 divided by 1900, so that's 2.37. So the value of the distance is 2.37 times 10 raised to negative 2. The unit is in meters. So that's our final answer, and that's it.